Okay, today we'll take up this bulk carrier, and OBO. There is another term also used, OBO, that is ore and bulk oil. Essentially, bulk carrier, as you can see, the name is in which we carry cargo in bulk, because now we are looking into the structural arrangements precisely that we have in the midship section region. We have seen that primary purpose or primarily structural arrangement is decided based on the strength requirement, such that it can sustain the loads, service loads. But at the same time, we are seeing that from the functional requirement, that arrangement changes, right? So what happens in case of a bulk carrier? Bulk carrier, as the name you see, that it carries cargo in bulk, so it has a loading pattern, as well as I'll have to think of how unloading will be done, right? So loading and unloading are two important aspects also of cargo, because if we have a mechanism by which I can load the cargo faster as well as unload the cargo faster, it's better. Why? Because then I need minimum dock time, minimum port time, because I won't have to keep the vessel long waiting in the port, because that costs money, right? So in bulk carrier, the cargo is in bulk, means the cargo would be just poured in bulk within the hold. That means schematically it may look something like this. Say you have the vessel, and let us assume the vessel cross section or the midship section is conventional, like we have seen in the general cargo carrier. In that case, we will not see this, we will rather say just the hull, outer hull is there, and as I have said, we need a double bottom to have a flat surface, and then the deck, and then we have the hatch opening, right? Now, if cargo in bulk, that is, say for example, salt has to be carried. So how it is carried? Generally what happens is it is transferred through a conveyor belt, right? So here salt is there, it rotates, so it will be directly being loaded in the hold. So in the process, what will happen as it grows, so the salt heap will form something like this. In the process, we see that this particular space remains unused, right? Same thing while unloading. How unloading is done? It is done either by sucking through a hose or by means of grabs. So again, same thing we'll find that part of the cargo will remain in the corner like this, because it will not slide down. That is the very property of that particular, at what angle it will remain or what angle this heap will form, all those things depend on, cargo to cargo it will be different. This is referred to as, this particular angle is referred to as angle of repose, right? So if the vessel is designed to carry, say, sugar or salt or wheat, depending on what each of those material has certain angle of repose. So if it is a multi-purpose kind of thing, that means in one voyage it takes sugar, the return voyage it brings wheat, right? So one can decide upon the average angle of repose, such that that average angle of repose can be decided, right? Now what is to be done? Here we see that this space remaining empty. What is the problem if it remains empty? Because that is not a loss of space, that by loading it up to this point, it's already attaining my what you call the loaded draft, right. That means in any case this space has to go empty, but if I just keep that empty, will there be any problem? While what happens is, I mean, if that remains empty as such, it does not have any problem.
So while healing the cargo,
yeah, the cargo shifting may take place. That means while it's sailing in the sea, and if the weather is fine, there is no untoward motion of the vessel, then no problem. But if it suppose faces a little rough weather and the vessel starts rolling, there can be cargo shifting to one side. So if cargo shifts to one side, means it will remain in a permanent heeled condition, which is called, it will have a permanent list, right. If it has a permanent list, then it will have directional problem in directional stability. It will not go in the straight direction. You have to give a rudder angle. That means there will be wastage of power. Similarly, when unloading the thing, if this much amount of cargo remains, what is the problem? Definitely, this is a direct problem we can see, because in the next voyage, if I are carrying something else, that gets contaminated. And if you want to really unload it manually, then the all purpose is lost. Means your unloading time increases drastically. So these are the problems. So if that is happening, the best solution would be if I can cut it off. That means put a plate like this and put another plate here like this. Cut it off simply. So thereby we come to the section shape like this. So what happens in that case? Here we have the cargo loaded like that, right. The entire cargo is there. So while loading, automatically this corner is taken care of, while unloading, again this corner is taken care of. It has been given a right amount of slope such that it will slide down, right. And thereby the form comes. So we have got in the process one space here, which is referred to as top wing tank. Because this forms like it forms a tank like structure, right. So that is referred to as top wing tank. Similarly, here this is bottom wing tank. It's at the sides, so they are referred to as wing tanks. And the dowel bottom remains as it is. As we have seen in other cases, the dowel bottom construction is same, right. Only thing, the length of the dowel bottom has become less. It has gone up to the one of the side girders. Here this side girder is a watertight girder, means same as that of the center girder. If I have a center watertight girder, this side girder is also watertight. Why? Because it's forming a part of the boundary bulkhead for the bottom wing tank or boundary bulkhead for the dowel bottom. So I have individual 3 sets of tanks: the dowel bottom tank, bottom wing tank and top wing tank, right. And here you have the cargo hold. So since these are all tankage spaces, so I have all of them longitudinally stiffened. You can see all are longitudinally stiffened. Dowel bottom is longitudinally stiffened, bottom wing tank longitudinally stiffened, means longitudinal framing system has been applied in all these, because they are all tankage spaces. They may go empty, that is immaterial, but if it is decided that this particular tank and this particular tank will be used for say ballasting or fuel oil or fresh water some purpose, okay, they can be used. But obviously these spaces are not used for cargo carriage. They are not for cargo, only for ballasting or fresh water or any other such purpose, fuel oil, right. So what you see, the construction of these wing tanks, they are similar to that of the floor. Only thing similar to that of the double bottom. Only thing there we have this plate floors as transverse member. Here we have a transverse member like this, which is referred to as, the top one will be referred to as top wing tank transverse, right. just a transverse, that is top wing tank transverse, means it's a plate, it's a transverse plate. In this, what you can see, so here you will have those scallops cut at the corners, right. There is scallops for the longitudinals. These are the deck longitudinals. These are the sloping bulkhead longitudinals, right. This will not be T section, it is only angular section itself. This is my side shell, part of the side shell within the wing tank, which is longitudinally stiffened, right. All these will have those scallops. So this is in the transverse plane a plate which is referred to as top wing tank transverse. That plate is giving support, that is the transverse member supporting the longitudinals. And for its own stiffness, these are my struts, like you have in the floor the struts, right. Same thing, similarly these are also the struts, right. And this green line here I have drawn, it refers to, that means a opening has been cut, which is reinforced by a flat bar welded all around, because the opening, if I keep unstiffened, then there will be lack of rigidity. Like you may have observed those tumblers which you have, the plastic tumblers which you use in bathrooms, the top, the edge is not just cut, edge is folded. Why? That means given a flange, so the edge becomes stiff. You just cut it off, then it will not have the stiffness. Same thing, same logic applies here, that you have the it is stiffened. Similarly, something at the bottom wing tank. So what we see is that the structural arrangement is essentially, you will have stiffening arrangement, means first we will decide on the stiffening arrangement, whether longitudinal or transverse. If we find that providing longitudinal arrangement is not any way obstructing to any of the functional requirements, then we go for that straight away, right, because that gives me better critical strength, buckling strength, better strength to weight ratio, right. So that is how it is done. Now we can see a part of the side shell is remaining yet to be stiffened. So what do you think the stiffening arrangement should be? Logical. Why not longitudinal? Because here, well, I am not carrying in the general cargo ship, we have talked about that we have provided transverse framing. The logic we gave that if I provide a longitudinal framing, the side shell longitudinal framing, that means if I have the longitudinals like this, right, then what happens? I will have to provide for a transverse frames almost double to that of the depth of the longitudinals, right, like this. That is needed because these longitudinals are running from one bulkhead to the other bulkhead. So you need support, you will have to cut down the span, sort of, not physically cutting down the longitudinal, but bringing down that L component smaller, otherwise your bending moment will be high, your scantling will be huge, etc. So if that happens, then we said that in general cargo ship we are getting only this much of cargo storage space, because what happens if you see in a plan view, say this is my, I mean, let us assume between two bulkheads, the side shell, if it is longitudinally stiffened, then what will happen? It will go, the longitudinal will go like this, isn't it? And the longitudinal and this transverses will be at every fourth frame space will be projecting like this, right. So thereby we can see my cargo storage space becomes virtually this much. This space gets wasted. But as far as bulk area is concerned, what is the problem? Because here I do not have, there the in case of general cargo ship, the cargo pattern are generally like this, right. It will be boxes or rolls of different size and shape. So, if I have this frames protruding from the side shell, definitely I am going to lose this space. I cannot utilize, because say the box is such a size that between those wave frames I cannot put it in, and if I really have to maneuver my cargo within the cargo hold, then your loading time further increases, right. But as far as bulk cargo is concerned, this is a bulk cargo is something like that of a liquid cargo. It can go in any nook and corner. So, I can as well have long channel priming. But do we have long channel priming? Is there any other problem, difficulty? We actually have transverse priming. Why? Can you tell me what would be the problem if I put long channel? Problem is simple. If I put long channel framing, they will form as shelf. A kind of it will act like a so called shelf, this, right. So, cargo will remain here. The longitudinals will be running all along the side shell, like here I have drawn, right. So, all along this cargo will remain stuck on this, because they will form like a shelf. Whatever be the dimension of this stiffener, say 300 millimeter, it can be 400 millimeter, depending on how big your vessel is. So, it remains. Suppose you are carrying sugar, so much of sugar remains. It's not important that that much of is getting lost, because again unloading you cannot do, because manually you cannot afford to do that. So, two problems. One is some amount of cargo will be lost, will remain there. Second, next voyage you are carrying salt, so it's a contamination of this. And third, continuously some cargo is remaining, so corrosion will be very heavy, because that place will remain continuously wet. So, there will be corrosion problems. So, because of these problems, side shell is transversely stiffened, right. So, bulk carrier side shell is also transversely stiffened, and the bracketing arrangement goes something like this. Right, the side shell. So, that is how we have the arrangement, a midship section arrangement for the.
So, does the longitudinals in the top wing tank and the bottom wing tank do not need support transverses?
Yeah, these are the transverses here. This top wing tank transverse, this what I have drawn, this is a plate, this is a transverse, you know.
It will be repeated 3 to 4 times.
Yes. Always, I mean, what happens is, if I see in the profile view, say this is my profile of the bulk carrier. Let us assume we have aft engine room. This line refers to the double bottom, right. Let us assume only 2 holes are there, as if, right. So, here this line will refer to the bottom plating of the top wing tank, right. This line refers to the edge of the sloping bulkhead of the bottom wing tank. This line refers to this, and this dotted line refers to this particular point, the sloping bulkhead of the bottom wing tank. So, this is how the tanks are going, and we will have those transverses, these transverses they are in one plane, the top wing tank transverse. In the same plane you have a side frame. In the same plane the bottom wing tank transverse, same plane plate floor. The very next frame, because every frame space some stiffening is there, very next frame what it will be? There will not be any transverse, there will be a smaller frame, side frame, is a smaller side frame. This black one what I am drawing is the normal side frame, the green one is the wave frame, that is called wave frame. Green one is the wave frame, means its scantling is little higher, whereas the black one is at the frame space where it is just the, it can be referred to as side frame or side cell frame or hold frame. So, what I am saying, it is like this. Let us assume that this is my, here I have a floor, all these transverse members in green I am drawing, this is my plate floor. In the same plane you have the bottom wing tank transverse. In the same plane you have the wave frame, top wing tank transverse, right? In between what is that? In between there the bracket floor, right? Here there is nothing, normal frame, again nothing, nothing means equivalent to that of the bracket floor. In bracket floor what was that? That, as you can recall, that only two brackets, only at the edges two plates were there, as if two brackets. Same thing happens here, only this much of the plate would be there, this plate, and here this corner plate. This is a strut I have drawn. So, when you have a bracket floor, similar arrangement in the wing tanks. The idea is that these are provided, this is my plate floor, right? In the same plane you have the wing tank transverse, right? And in the hold you have side shell wave frame, right? Whereas so in that way you have the bulkhead. So, at the fourth frame space you have a total ring of plate floor, transverse, wave frame, transverse. So, as if these green lines are as if forming the ribs at intervals. What interval? 3 to 4 frame space. To be very precise, different classifying society they spell out not more than 3 meters, not more than 4 meters, some such thing spacing. What does that mean? That means the any longitudinal member going, its span is not more than that. It's not more than that, not more than the spacing between two such rings, right? So, here this is your bracket floor. Okay, let me write from this side, because then that gives you a similarity. This is my bracket floor. Then in the wing tank transverse, only wing tank brackets, right, and ordinary hold frame. not wave frame. Okay. So, you will have 3 to 4 sets of such bracket floor, wing tank brackets, ordinary hold frame, then you will have one plate floor, wing tank transverse, wave frame, right. So, that is how it goes. Okay. Right. So, this is what is the structural arrangement, midship section structural arrangement for the bulk carrier. And obviously, on the deck you have here is what is referred to as your bulwark, right. Here you have the hatch combing, right. This is what is, these are all you will have in all vessels. This is what is bulwark, this is your hatch combing. Okay. So, we see here that in this case in the bulk carrier, because of depending on the functional requirement, your entire structural arrangement has been changed. And here we see that we take advantage of longitudinal framing in all the tankage spaces where there is a possibility of some liquid being carried, not liquid cargo. Liquid means some functional liquid, right, fuel oil or ballasting, like that. And in the hold, in the side shell part of the hold, well, it is transversely stiffened. For the reason, again, if I have longitudinal framing system, then that will hamper in sort of, that may lead to cargo contamination, that will lead to longer I mean your unloading time, will lead to higher corrosion rate, right. Another aspect you can see here, that the side shell frame, which is connection details are, it is connected with a bracket to the sloping wing tank bulkhead. This particular plate may be named as sloping bulkhead. Sloping bulkhead is the sloping bulkhead of the bottom wing tank. Similarly, this one is the sloping bulkhead of the top wing tank. All right. Here you can see the sloping bulkhead is coming and having a horizontal plate at the bottom of the top wing tank, a horizontal plate, but the bottom wing tank sloping bulkhead meets directly to the shell. You do not put any horizontal plate there. Again, for the same reason, if I put a horizontal plate, cargo will remain. So, these are very simple and but detailed issues, because one will tend to replicate whatever is there in the top wing tank just in the bottom. And for information, the most I mean earlier bulk carriers used to have like that, because if you have that way, then intuitively, right, you know, because this comes like this, right, intuitively it is done the same way. Right, and also you find that your bracketing arrangement etc. becomes more convenient, as if isn't it? But this space then creates a problem. So, it is not done like this. Instead, it goes and meets straight, such that that slope remains. Okay. And the bracket is connected, and you can see the bracket toe of the bracket lands on a stiffener, on a longitudinal of the sloping bulkhead. You will not terminate it in between, because you terminate in between means what? That place gets heavily loaded, there is no support below, because this bracket is acting as a increasing the load distribution area, right. Because you can have a feeling that this wing tank as if is hanging over this, as if it is a cantilever type of structure hanging over this side shell, which is stiffened. This entire structure is being supported by a shell structure with vertical stiffness and these brackets. So, that load, entire load comes and gets distributed over it. So, here also you will have to have the stiffeners, this brackets landing over the stiffener, the toe of the bracket. Yeah. Well, one of the problem this bulk area structure they face is after a few years of service, this region, this bracket at the bottoming tank, it gets corroded heavily, right. That is one of the main problem of maintenance problem of this bulk carriers. Can you tell me why this part corrodes? I mean, not other part. There will be corrosion in other parts also, but that is much lesser degree. Here it corrodes so heavily that if proper care is not taken, even one may find that total detachment of the bracket has taken place. Detachment means essentially what is done, that this place is welded, isn't it? This is welded, right. So that entire joint has got detached. I mean, there is a physical gap between the bracket and the sloping bulkhead. Because what happens, this part is welded, though there is no cargo remaining there, but enough dust particle remains stuck there, compared to the, say, this bracket is also welded at the top, at the bottom plate of the topping tank, but that plate doesn't corrode at all, virtually doesn't corrode. But here what happens, those enough of dust particle remains there, enough of salt grains remains there, right. So that way this place remains continuously moist, and all this dust and salt, whatever, they are hygroscopic in nature, so continuously moist, and that moisture that forms the galvanic cell, that gives a I mean, that moist dust, it works as the electrolyte, right. And well, since this is welded here, so all the corrosion prevention mechanism, that means proper painting, etc., is also difficult. Difficult means not up to the mark as compared to other plain areas. So deterioration, I mean, the corrosion sets in much faster at these places, and the rate of corrosion is also higher. I mean, in addition to that, you have problem of, since it has been welded, you have residual stress. So the stress level is high, that leads to further rate of increase in the corrosion rate, right. All this leads, so that this is one of the major problem for bulk areas, this bottoming tank, this bracket, that bracket detachment takes place. So that is what is bulk carrier. And now another, along with bulk carrier, we have talked about the OBO carrier. OBO is ore and bulk oil. I mean, that is how it is named. In this particular vessel, we had been talking about cargoes like sugar, right, salt, pulses, all right, wheat, like that, rice, maybe, all in bulk, in loose, right. Now also ore is carried in bulk, like say iron ore and other ores, right, manganese ore or whatever. So can we carry those ore cargo also in this bulk carrier? What do you think? Physically, yes, because I can carry. What would be the basic difference? I mean, say in one voyage I am carrying sugar, and in the next voyage, suppose I am bringing back iron ore in the same vessel. What would be the basic difficulties one may face, if any? First is obviously contamination. I mean, contamination the other way. That means, suppose again in the next voyage, say the cargo pattern is such that some country is say I am importing sugar and exporting iron ore. If that is the trade, same vessel I use. So when I am bringing back iron ore, whether it is mixed with some sugar doesn't matter, but the reverse, it matters heavily. You cannot do. That is number one. What is the number two? Second problem. Well, one may say that I will clean it thoroughly, which is again not very wise. But what could be the other problem?
The load distribution will not be continuous. Load distribution in the case of water.
Why? No, I can.
In case of sugar, it will be very distributed uniformly.
You mean to say in the hold, right?
Yeah.
No, in ore also, I mean, look from that perspective, the sugar is very fine particles, each particle. Well, here the each particle maybe will have much bigger dimension, but overall when I take, it is also a fairly good uniformly distributed load. I mean, that will not matter much. What you are saying that basically, like it is one extreme is the liquid cargo, is absurdly uniformly distributed load. Another extreme could be coal or ore kind of thing, where the chunks are of different size. So, but overall average it will be fine.
The weight will be different.
What weight? Doesn't matter. I mean, thing is that it is. I have my load water line here defined. That means beyond that I cannot load. So I go on loading, and when I find it has touched the load water line, I stop my loading. So it has taken in, suppose the bulk carrier is designed for carriage of 60,000 tons of cargo. When it touches this line means I have achieved that 60,000 tons. The difference would be, in case of sugar, it will get filled up like this. In case of ore, it will get filled up only like this. This would be the probably the ore, and if I take sugar, well, this is little exaggerated, but still. So, what is the basic difference? Means density of the cargo is highly different, substantially different. The order could be 6, 5.
So shear will be more.
No, that's a different thing. I load in all holds, so there will not be much problem of shear. If I, yes, that is coming next. I mean, so what is happening? If I put ore, then hardly some space it will occupy within the hold, isn't it? Hardly some space will occupy. Say at best it will occupy this much, right? And so much of space will remain empty. So, what is the problem the vessel may face? That again, shifting of cargo, right? Shifting of cargo, when you are plying the cargo may get shifted, and the same problem will be there of listing, right? So, what would be the solution? One solution could be I fill up alternate holds. One solution could be alternate hold. Then I can fill to a much greater depth, right? So, then that shearing problem will come. If alternate holds are filled up, then what is happening? Physically, it would look something like this. That means, say here I have well, cargo loaded, empty, again cargo loaded, empty, like that. So, here you will be having huge loading, and here only the buoyancy force is acting. So, there will be shearing problem in between this. So, that is not also not a good solution. So, then what to do? And another aspect also you can see, another aspect what happens, because the cargo is very dense. So, your CG ports position also comes somewhere here, right? CG position also goes down, and once your CG is much low, I mean physically location is low, that may lead to that value GM high, because your position of the metacenter is dependent on the geometry of the outer hull, right? It's irrespective of what cargo or what you are carrying, it's geometry of the hull. So, M is fixed somewhere, right? So, that will lead to a very a ship which may have a very high frequency of oscillation, means rolling period will be low, it will roll very faster. That is referred to as stiff. The vessel is stiff. Vessel is stiff means your rolling period is low, means it oscillates faster, so it becomes uncomfortable for the crew, as well as dynamic loading. The dynamic loading in the structure increases because it's oscillating, means is executing some acceleration in the motion, so forces are generated, right. So it will lead to, well, one is physical discomfort for the crew, then higher possibility of failure due to fatigue, right, all these things, and also higher possibility of ore cargo shifting to one side. So what is the solution? Solution is that you cut it off, make a arrangement something like this. Means what has been done, if I compare with the bulk carrier, the top wing tank and the bottom wing tank, we have added a side tank also. Assume as if here there was no side tank as such. Suppose I have a bulkhead here, right, a bulkhead here, then it becomes a side tank and this volume becomes less. As well as I raise the double bottom height, increase the double bottom height, add a side tank, thereby I make this space smaller. This is my cargo space. So when iron ore is being carried, I carry only here a small space, and what happens, that way I achieve the necessary draft, means it is loaded to the full draft, okay. And since it is nicely filled up the cargo space, so no question of cargo shifting, and those problems is solved. Then what about the GM? GM is also well taken care of because I have increased the double bottom height, thereby position of G has gone up, right. Position of G has gone up because I have increased the double bottom height. So the vessel will not behave the same way otherwise it may have behaved if I would have taken ore or high density cargo. It's not the question of only iron ore, it's low density cargo, high density cargo, right. If I would have carried a high density cargo in the ordinary bulk carrier. So that is what is done. And now I have another added advantage is that I have a tankage space, entire tankage space on the side. So in one voyage I can carry ore, in the return voyage I can carry oil, some kind of oil, some kind of liquid, right. That is the advantage, because otherwise in suppose it would have been a bulk carrier, then if I carry iron ore in the return voyage, I will have to carry either coal or equivalent, some such product. Nothing else can be carried, not even oil, because they will contaminate, right. So here my two dedicated places remains this place. In one voyage I carry ore, return voyage here I carry oil. So this is sufficient space. Also the draft utilization, the capacity utilization will be fairly good. Though, well, now the question comes whether now really I can use this for what kind of oil? Crude? Probably no, because in the event of accident I do not have any protection. Now there are, from the pollution control point of view, in oil tanker also you will have to have a double wall, a double bottom, and all those restrictions are there. So if I provide a double wall here, then again it doesn't make any sense, right. So probably edible oil, well, in bulk edible oil can be brought, because even if that is leaked, cargo loss is there, but not pollution. So some such. So this is one of the way. Or, well, the vessel comes empty, at least you are saved from the problem of higher GM, saved from the problem of directional stability, right. So, this is what is ore and bulk oil carrier, which is written as OBO carrier, right. And also here you can see I have just drawn the shown the framing system. Since this entire part will be some form of liquid will be carried, so you have all longitudinal framing system, entirely longitudinal framing system, and obviously at intervals in the transverse plane you will have transverse members, right. You will have transverse members, and also you will have platforms in between, right. That means horizontal platforms within the tank. The reason is simple, these are for, because if they are not there, then can you imagine how we are going to maintain the entire structure, because maintenance is required. If anything is happening to these longitudinals or some corrosion is taking place, some repair, so these will be horizontal platforms such that people can walk through this, right. That is how the structural arrangement will be done. That means, so what we see that the structural arrangement are done based on functional requirement. Second, first and foremost, well, structural arrangement is based on the criteria of strength, also on functional thing, and here these we have added from the maintenance point of view. Maintenance requirement means the structure, because as we can see that if you only care for your what you call strength requirement, then you have some problem in loading, unloading, storage of cargo. That means it is interfering with the functional requirement. If you take care of both, then again we see this is one of the case. Similar thing we will see in some other vessels also, that from the maintenance point of view again it becomes a huge problem, because if I do not use such horizontal platforms, then accessibility is not there at the top part of the structure, right. So, these platforms I am providing for keeping in maintenance in view, but also they are providing strength, because they will be part of the strength members also. They also will be part of the strength members, though functionally as such is not required, but functional from maintenance point of view again they become useful. So, that is what is the bulk carrier. Okay. So, next class we will look into container ships.